Recording on this computer. Okay, welcome back, Chemistry 2330. This is our final lecture. We have one exam, which is on, Thursday, and then we have our final. Let me go ahead and pull up our schedule here. According to my results here, we have a review today, and I'm going to start with chapters 12 through 16 because that's going to be on the exam 3, which is on Thursday the 29th. And then I will also continue with chapters 1 through 11, which are going to be on the final, which I have is Thursday, May 6th from 11 to 1:30 p.m. Of course, both of those are going to be given on Top Hat, so we don't come here on Thursdays. Those next 2 Thursdays, we go to Top Hat and go ahead and take the exam there. If you're having issues, I'll be live monitoring, of course, and you can just email me and we'll try to get all that taken care of. Any questions on when our next 2 exams are? Okay. So we have gone through a lot, right? We started with just what in the heck is an atom, to what forms the bonds, to shapes and everything like that. But what I hope you found is there's a certain order to the organic chemistry. We have our nomenclature, which follows the same pattern all the time. Most of our reactions, we're looking for what's the nucleophile, what's the electrophile, what's the acid, what's the base. And most of the reactions we talk about can be defined in those things. You can look for, ooh, this is the partially positive charge, or this is the positive charge, or these are the lone pairs, or this is the negative charge. There is order to organic chemistry. And as you study for this exam and the final, I want you to kind of think about, oh yeah, that's like this, but different. That's like this, but a little different. And you'll start to see these patterns arise, okay? So we did 16 chapters. And if you take the follow-on course of biochemistry, it's great. I think we were quite prepared with all the different reactions we need for that. If this is your terminal organic chemistry course, I hope you learned a lot. And I hope that you can take some of this forward and start looking at your shampoo bottle and say, hey, you know, I understand half of these chemicals. I know what they look like. So that's kind of one of the points, is to make organic chemistry accessible and make you not scared of it. So I hope that came through in this semester's course. Okay, so let's start with the review for our exam on Thursday, exam number 3. We're going to do 12 through 16. So in 12, we started talking about the set of chemical compounds that all had carbonyls in them, okay? So that was the common theme running through 12 through 15, is that carbonyl, okay? And we use them in several different ways, okay? In chapter 12, we introduced the concept that our carbonyl has if it's bonded to hydrogens and carbons, it had certain properties, and those are our aldehydes and our ketones, okay? But then when we started changing that carbon or hydrogen out for oxygen or other electronegative atoms, we got different reactivity in the carboxylic acid and the carboxylic acid derivatives. Okay, so let's go over our aldehydes and ketones first. So in our aldehydes and ketones, we see that if there are 2 carbons bonded to that carbonyl, it's a ketone. If there's 1 carbon and 1 hydrogen, that's a substituted aldehyde. But the simplest aldehyde is with 2 hydrogens on it. And we actually use those 2 hydrogens in a follow-on chapter where we reacted it with a Grignard reagent to make a primary alcohol. Now, the whole reason this works is that we have that partially positive carbon and that partially negative oxygen, giving it reactivity and selectivity. Our nucleophile will always attack that partially positive carbon. And those are many of the reactions we saw. With aldehydes and ketones, we saw addition reactions because there was no good leaving group. A hydrogen negative or a carbonyl, or a carbon negative are not good leaving groups. In the carboxylic acids and their derivatives, we started seeing substitution reactions. We had things that were getting less and less basic and therefore were easier to remove, and we got substitution reactions. So aldehydes and ketones typically do addition reactions. The carboxylic acids typically do substitution reactions. Okay, so what we learned in this chapter was also that we have an organometallic reagent specifically called the Grignard reagent. The whole point is we have a covalent carbon-magnesium bond, but Because magnesium is less electronegative than carbon, carbon carries the negative charge, turning carbon into the nucleophile. And we use that to attack various carbonyl compounds to make primary, secondary, and tertiary alcohols. Okay, so if we attacked formaldehyde, we made a primary alcohol. If we attacked any other aldehyde, we made a secondary alcohol. If we attacked a ketone, we made a tertiary alcohol. And so we can actually choose what we want from those different things. Okay. We also learned that there is an equilibrium between having the ketone form and having what we call the enol form, or an alkene alcohol. Now, the equilibrium typically lies to the carbonyl, but the fact that it does do this gives us rise to certain types of chemistry, specifically halogenating on this site. And it'll only do that because of this little bit of enol keto tautomerism, and the fact that we can see that, the fact that those reactions work, proves that we do have a little bit of that enol form present in the ketones. What we also learned is how to make aldehydes and ketones or carboxylic acids by oxidation. So if we have a strong oxidant like chromic acid, it'll oxidize alcohols to either aldehydes, ketones, or carboxylic acids. But remember, to stop at the aldehyde, we have to use that special reagent PCC, pyridinium chlorochromate. Okay. We also learned that we can specifically reduce down the carbonyl compound by using a nucleophilic hydrogen, using a hydride. There's a negative charge on that hydrogen, so it specifically attacks the carbonyl compounds and not alkenes. So we have these two specific materials that we have. Sodium borohydride can reduce aldehydes and ketones down to alcohols. The lithium aluminum hydride, we found out, can do esters and carboxylic acids also. So it's much stronger than the sodium borohydride, and we got to see it all reduce them all down to alcohols, either primary alcohols or secondary alcohols. All right, questions about chapter 12. Okay, so that carbonyl carbon is, all the reactivity happens because nucleophiles are attacking the partially positive carbon. Okay, that's the unifying theme in the entire chapter.
Does the lithium aluminum hydride, that won't reduce an alkene, correct?
Correct. It will not reduce an alkene.
Okay.
But, and you can reduce down the carbonyls with hydrogen and palladium, but that'll do the alkene and the carbonyl. These just do carbonyls because it has that negative hydrogen attacking the carbon. Okay. So this chapter, again, that overlying theme on this is the fact that there's that partially positive charge on carbon and it's being attacked by nucleophiles. All right, and then we moved on to chapter 13, was carboxylic acids. And we learned that we have some dicarboxylic acids that we would name dioic acids, but they also had common names. Oh my, such good apple, and then pi would be for the dicarboxylic acid of the benzene ring, which we learned about in the previous chapter. Okay. And we learned that these carboxylic acids increased in their acidity by having electron withdrawing groups pull more electron density away. And remember, the acidity is increasing because you're making a more stable anion. The more stable that anion, or the more that charge is spread out over more atoms, the more acidic it becomes. It's easier to lose that proton. So think about it as the more stable the anion is, the faster the proton is going to leave. I guess faster is not the right word because it's thermodynamic, but the easier it is for that proton to leave, and therefore it becomes more acidic. Okay. So what we also learned in the carboxylic acid chapter is that lithium aluminum hydride will reduce down carboxylic acids and aldehydes to their alcohols, but only with the lithium aluminum hydrides. Okay, the sodium borohydride is not strong enough. And then we took advantage of that enol keto tautomerism that we learned about in the previous chapter for looking at a way to easily decarbonylate something. But you had to have a ketone in that beta position. Carboxylic acid with a beta ketone allows you to form that six-membered ring, which kicks out that enol form of the ketone, which of course rearranges to give us our ketone and CO2. So literally we've caught one carbon off of this chain and removed it as CO2, and we are left with just the ketone. So this decarbonylation reaction is specific to these beta carbonyl carboxylic acids. It's very hard to do it otherwise, but because of this transition state, it does happen. Okay. So then we went on to learn a little bit more about their derivatives. Okay. Now, carboxylic acids do substitution reactions because they have better leaving groups. In the case of the carboxylic acid derivatives, we have chloride as a leaving group, or a carboxylic acid as a leaving group, or an alcohol as a leaving group. Those are much better leaving groups than the hydrogen, the hydride, or the carbon anion. Therefore, we get substitution reactions, not addition reactions. And so that's the big difference between the carboxylic acid derivatives and just the aldehydes and ketones. It's that ability to reform the carbonyl because you had a good leaving group. What we also found out is that they all had kind of different reactivities. They all react with water, but to a different degree, okay? And so we found the chloride is the most reactive. In fact, we can make all the other species from the chloride, okay? But when it reacts with water, it turns into a carboxylic acid and water. The anhydride also reacts with water and turns into two carboxylic acids. We can use that anhydride to make esters or amines. But then when we got to the esters, we found out we needed some kind of catalyst to drive it. We couldn't just heat it with water. It wouldn't really go very far. So we found out we could catalyze it with acid because we regenerate the acid. But in base, it's mediated. We have to use an entire equivalent of base to make it do that. So it actually forms the carboxylate salt as it forms. So the acid is catalyzed, but the base is mediated. It takes an entire equivalent. Okay. So, and then we found out amides are the hardest to do, okay? And in both cases, they are mediated. Neither one is catalytic because we create a salt of either the nitrogen portion of the amide or the carboxylic acid portion, depending on whether we use acid or base. So the only one of these reactions that's catalytic is that acid catalyzed hydrolysis of the ester. But yeah, or the transesterification, which we also do. But in hydrolysis, that's the order of reactivity from top to bottom, and the necessity of having mediation in all of these where we can have catalytic in that one. That's how to kind of organize these kind of reactions in your head. Okay, so from that, we can make either esters or we can make carboxylic acids or anhydrides from these different things. In this case, we're making esters from the acid chloride by just adding alcohol. We're making esters from other esters by the transesterification reaction. We can make esters from anhydrides just by adding alcohol, but you cannot make an ester from an amide. The amide is not reactive enough. Amides, you can make amides from acid chlorides, anhydrides, or esters, but you cannot make a different amide from an amide because it's not reactive enough. So that order of reactivity is one of the things we need to remember about that chapter. And the great way to remember that is this table. So if you think of this as the most reactive, you can make any of these species from that acid chloride. You can make any of these from the anhydride, any of these from the ester. And the only thing you can make from the amide is that hydrolyzing it to the carboxylic acid or the carboxylic acid salt. And then once you have the carboxylic acid salt, we can actually make the acid chloride with thionyl chloride. So in the aldehydes and ketones chapter, we learned that Grignard reagents react with aldehydes and ketones. And we learned in the carboxylic acid chapter that they also react with this ketone. I'm sorry, Grignard reagents also react with carboxylic acids to generate primary alcohols. And again, in esters, they do the same thing. But again, it takes 2 equivalent for a carboxylic acid and 2 equivalents for the carboxylic acid ester, and it'll substitute twice to get you down to an alcohol. Again, in the carboxylic acid and in the ester, we have attack of a nucleophile on that carbonyl carbon. Okay, so let's see. And then the next thing we learned is that lithium aluminum hydride is strong enough to reduce esters down to alcohols, but sodium borohydride is not. So sodium borohydride only does the aldehyde and ketones. Lithium aluminum hydride will also do carboxylic acids and carboxylic acid esters. All right, and we can do an additional reaction where we can reduce down that carbonyl to get primary amines. When we did amines, it was very hard to get a primary amine, but it's really easy to make an amide. So you can make a primary, secondary, or tertiary amine, depending on whether your amide was primary, secondary, or tertiary. Okay. And then all you have to do is use lithium aluminum hydride. Again, it only attacks the carbonyl, giving you your final product. Questions about carboxylic acid derivatives? Do you see how we're using those same reagents in those different chapters to show that the same thing is happening in all of them? Lithium aluminum hydride is the only one that's reacting with all the carbonyls. The Grignard is also reacting with the carbonyl. So we should start seeing a pattern here. All right, which brings us to chapter 15. And we use the carbonyl in a different way. We're using the carbonyl as an electronic drawing group to increase the acidity of those alpha hydrogens, okay? And in those alpha hydrogens, we find that the order of acidity goes by how much electrons you can pull away from that alpha carbon. So if we look at alkanes, those are our least acidic, our alkenes are more acidic, and our alkynes are the most acidic of the hydrocarbons. That has everything to do with the hybridization and the amount of S character. Okay, but now when we have our first carbonyl compound here, that's an ester. That carboxylic acid is pulling some electron density, making this hydrogen more acidic than an alkynyl hydrogen. Okay, so that carbonyl is influencing it to be more acidic. And then notice that there's an oxygen here. So it can't pull too much away because it can pull some of the electrons from the other side. So by taking away that oxygen, it becomes more acidic. Now we just have carbons. And that carbonyl is able to pull more electron density and it's more acidic. Okay. So in the case of water and alcohol here, they're more acidic, but that charge robot, that hydrogen is on an oxygen. And that's why those are more acidic than the hydrogen on carbon. Now, how do we get even more electron density away? We pull it from both sides. So these diesters are the next most acidic. And then if we switch out one of the esters for a ketone, it gets more acidic because there's no oxygen to donate partially back. And then of course, that brings us to our most acidic of the dicarbonyl compounds, our beta diketone. So our beta ketoester and our diester here are less acidic because of those presence of those oxygens. Okay, so what can we do once we pull that hydrogen off? Well, we found we had three general classes of reactions, okay, which is the aldol reaction, the Claisen reaction, and then we did the Michael addition. Okay. So, but all of them started with the same thing where we pulled a hydrogen off an alpha carbon. In the aldol reaction, you use aldehydes or ketones, and you then initially form a beta hydroxy aldehyde or ketone. Okay. So that's the aldol reaction. If you heat that reaction up, it loses water and becomes an unsaturated aldehyde or ketone. If we have only one of the compounds having alpha hydrogens, that's a crossed aldol reaction because only one can make the enolate, and then that creates our nucleophile and it has to attack the other species. So that makes it for a cleaner reaction and a very easy way to make your beta hydroxy aldehyde or ketone. But don't forget, we can also make rings. If you can form a 5 or 6 membered ring because you have 2 aldehydes or ketones on the same compound, they will form 5 or 6 membered rings. 4 and 7 membered rings don't form. Well, they can form, but in a very little amount. 5 and 6 membered rings do that intramolecular interaction. And it's all about that stability of that system. Now in this one, we show that the intermediate is the hydroxy ketone in this case here, but then we also see it losing water. Remember, that's when we go from the aldol reaction to the aldol condensation because it liberates water from the reaction. Okay, now the claisen involves esters. So aldol is aldehydes and ketones. So think aldol is aldehydes and ketones. Claisen is all about esters. So you use 2 of the same esters and you'll end up with a beta keto ester. You always end up with a beta keto ester because one of your leaving groups is going to be alkoxide and it comes out and it remakes the ketone. Okay, that's why it works. We can also use a cross claisen where one thing has no alpha hydrogens, the other thing does have alpha hydrogens, and so you have only one way for them to react. And of course, we can close those rings again, just like with the aldol intramolecular condensation. We call it the Dieckmann condensation, but it's the same thing. But again, only forms 5 and 6 membered rings. Now we learned this in the carboxylic acid chapter, but in the case of this claisen reaction, we'll end up with a beta keto ester. And if we clip off the alcohol on the beta keto ester to turn it into a carboxylic acid, that gives us our beta keto acid, which we learned about in the carboxylic acids chapter, that you can decarbonylate it if it can form a 6-membered ring, giving us that enol form, which then immediately rearranges to our ketone. Okay, so in this one right here, we're again doing the exact same thing with the other. We're attacking a carbonyl with a nucleophile. In this case, it's a nucleophile created by that alpha hydrogen being acidic. It's the same mechanism, general mechanism for all of them, except that in the case of the ester, you can lose alkoxide and you gain your carbonyl back every time. In the aldol, you end up getting a hydroxide because that's a bad leaving group, but you can eliminate water to form an alkene, but you will not regenerate the carbonyl in the aldol condensation. Okay, and then the last of the set is we used it as a nucleophile to do what we call a 1,4 addition or a Michael addition. It's not attacking the carbonyl because we have a double bond in conjugation with that carbonyl. Because it's in conjugation, our partially positive charge at our carbonyl can be residing out here. So part of the time, because of conjugation, it'll go back and forth, and therefore our enolate will attack at that position, and we get that, what we call that Michael addition reaction. We're adding on to the end of the chain, not on the carbonyl. But it's because the carbonyl is there that we get the partially positive charge on that carbon. So it's directly related to that partially positive charge on carbon. So when we do that, we always have an unsaturated aldehyde or ketone or ester. So it has to be in conjugation, like with our carbonyl. And then we use some kind of usually difunctional enolate or even an amine. An amine is enough of a nucleophile to add across it. And we get a slightly different product there. We get that extended amine product. Okay. And then once you get this, we can actually do that decarbonylation again because we're going to get a beta ketone. that beta ketone ester here and then a ketone over here. And by doing our thermal decarbonylation, we can get to a diketone. So now we've gone full circle from where we started with the carboxylic acids, that decarbonylation reaction with the beta keto ester, to using a Michael addition to get to a diketone. Okay, so that kind of pulls us all the way back around to chapter 13. All right, questions on reactions with those carbonyl compounds? Okay, so then polymers, the most important things are the idea that you know that they're very large molecules, and we have two different types of mechanisms. We have what we call step growth mechanisms, and when you think about that, think of a functional group other than carbon-carbon somewhere in the name. An amide, an ester, a carbonate, a urethane. Those are functional groups that are not just carbon-carbon bonds. So, and they're typically made by having alternating two functional groups, and then they start building and building and building. One adds at a time. That's why we call it step growth. Okay, and we had amides that included nylon 6,6 and nylon 6, as well as Kevlar, which is the aromatic version of it. But when we made esters, we typically don't just take a carboxylic acid and a alcohol. We typically do a trans esterification. We use an ester and an alcohol, preferably a higher boiling alcohol, and we heat them together with a catalyst, and it drives off the low boiling alcohol, creating your ester. But that makes some nice things like PET, where that can make nice fibers in certain bottles. But to be really, really tough, we got to move to the carbonate. And the carbonate is like having two esters on the same carbonyl. And that's where we get our Lexan. That's where we get our safety glasses. And then we have urethanes that are made from isocyanates and some alcohols. Think rubbery, pliable, and foams. And then we get to the epoxies. The epoxies are the ones that are hard, fast, and what we call thermosets. Once they react, they don't go back. All of these other ones, we can use mechanisms to get them to dissolve or melt or flow. Epoxies don't. You can't dissolve, melt, or flow epoxy after you've done it. So that is step growth, okay? Again, think anything with a name like, an amide, an ester, polyester, polyamide, polyurethane. That is going to be that system. Now, when we go to chain growth polymerization, think of only carbon-carbon bonds in the main chain. And we do that by starting with something with a double bond and then use a radical mechanism, okay? So we call that chain growth because the chain is going to be the one that's growing from the end, and it's not going to do two reactions, then those kind of float over here and react with another one, and then it's float over here and react with another one. This actually zips up the chain by that radical mechanism. Okay, now there are 3 steps in that radical mechanism. Initiation to generate your first carbon radical. Okay, once you've generated that carbon radical, it's going to take one of the electrons from the double bond and leave the other electron on the most substituted carbon, because radical stability is like carbocation stability. The more substituted it is, the more stable it is. That means it's going to add a specific pattern every single time. And it's going to keep doing that until you run out of double bonds. When you run out of double bonds, you terminate the reaction by having 2 radicals combine to form a sigma bond. Okay. It reacts much faster with the smaller alkenes because they're floating around much faster. As the chains get bigger and bigger, they're slower. But when you run out of other things to react with, they will react with themselves. Okay. So that's the mechanism of those chain growth polymers. And that's the important part here. So the step growth mechanism and the chain growth mechanism are probably the 2 most important parts of the polymers chapter. Okay, so that's the review of 12 through 16. Any questions about exam 3, which is 12 through 13? 12 through 16. Okay, Bueller. Okay. All right, I'm going to stop sharing that and pull up chapters 1 through 11. Share screen. Oh, I just have to change out the file. Now with chapter 1 through 11, we're going to talk about going all the way back to the beginning about hybridization. I harped on hybridization because it, number one, tells you how many electrons are available to bond. It tells you the shape of the molecule. It tells you the driving force on why things happen. Everything's trying to get to that sp3 hybridized reaction. That's the most stable. So that's why alkenes will always try to react to get substitution products, and alkynes will react that way because it's more stable. How many questions are going to be on there? There's going to be 30, just like the other exams. The final actually is 60 or 65 questions. All right, so know your shapes, know your hybridization. Okay, know your functional groups. I also have posted on Canvas the 1 through 11 review, the 12 through 16 review, as well as nomenclature. And I'll talk about nomenclature if we have time today. Okay. Know your functional groups. That's really important. And with knowing your functional groups, be able to recognize them visually. Okay, and be able to say, if I say, and you're taking an alcohol and doing this, you need to know that, oh, well, it's got an OH on it. That's where it's going to react probably, etc. Okay. Chapter 2, we talked about acids and bases. We used pKa's a lot. In fact, we used pKa just a couple minutes ago talking about why the enolates were more acidic than just regular alkanes or alkynes. Okay. So know that series of, I think there were 8 or so that you really kind of need to put to memory so you kind of know where they rack and stack. Then what we also learned is there's different kinds of acids and bases, right? There's the kind of acid and base that only works in water. And that was one definition. But then there was also, when we had organic compounds, we called them Bronsted-Lowry acids and bases. So they're organic compounds, not in water, but they still transfer the proton. But then we broadened the topic out even more to talk about Lewis acids and bases. And so we didn't have to transfer a proton at all in a Lewis acid and base, okay? So the idea here is a Lewis base is something with a lone pair or a negative charge, ready to use those electrons to make a sigma bond. A Lewis acid is anything that is lacking enough electrons and is looking to go and take those electrons donated by the base to make a sigma bond. So in Arrhenius, that works because of water. Water is the base and the proton is the acid. In Bronsted-Lowry, the acid is anything that's going to accept those electrons. The base is anything that's going to donate. The base is anything that's going to accept a proton. The acid's anything that's going to donate that proton. But it still falls under the Lewis acid base rules. So if you have to remember one thing, remember the Lewis acid, Lewis base. Lewis base has lone pairs or negative charge. Lewis acid has positive charge or a lack of electrons in its octet. Okay. Which brings us to nomenclature. Chapter 3. Know the different classes of compounds. We have alkenes, alkynes, alkanes. We have those aromatic species, which has their own naming structure. So you don't forget to study our benzenes in chapter 9. And then also remember some of the common alkyl groups. The propyl, the isopropyl, the butyl, the isobutyl, sec-butyl, and tert-butyl are the most common. The rules are enumerated here, and we use the same order every single time. Identify the functional group and their priorities, find the longest chain, try to get the lowest number, have each substituent given a name and a number, and then order them by alphabetical order, etc. But don't forget stereochemistry. Are there 4 different things on carbon? Then you have to use R and S. If you have an alkene, it's preferred to use either cis and trans if you only have 2 substituent, or E and Z if you have more. Remember that Z is on the same side, it's analogous to cis, and E is on the opposite sides, analogous to trans. Okay. Now, here's the order of precedence. Carboxylic acids are the highest order, so if you see a carboxylic acid, it's always named for that. Aldehydes and ketones are next, but if they're a substituent, you have to call them oxo. Then alcohols are either the alcohol or the hydroxy, and then chlorines and chlorines and ethers never change the name. It's always named for the hydrocarbon. Every single name has 3 parts. The prefix, that tells you all the substituents and the number of carbons in that longest chain. The infix tells you whether you have single bonds only, a double bond, or a triple bond, or a combination of the 2. The ene and the ine, that is there if you have double bonds or triple bonds. And then the E at the end is the suffix on hydrocarbons. That just means you have only a hydrocarbon. That end changes by your functional group. All for alcohol, al for aldehyde, on for ketone, and oic acid for the carboxylic acids. Okay. Know your priorities of carbons. It's how many carbons are attached to that carbon for degrees of carbon. So that means we can get 4 carbons attached to a carbon. So we can go all the way from primary to quaternary. Okay. Alcohols are a little different. We have a methyl. It's how many carbons are attached to the carbon the OH is on. So we can have a methyl, primary, secondary, and tertiary, but we cannot have quaternary alcohol because that would have a 4th bond to carbon, and that would be done. There's no place for the oxygen to be. Now, that brings us to amines and amines, which are backwards. It's how many carbons are attached to the amine. So if you have no carbons attached, it's just ammonia. It's not an organic compound. But if you have 1 carbon, it's a primary, 2 carbons, it's a secondary, and 3 carbons, it's a tertiary. Same rule for amines, except that first carbon has to be a carbonyl. And then the second can be just regular carbons. So that's, don't forget our naming structure on that. Questions about nomenclature? Okay. Again, this is for the final, but we have some nomenclature that we use in the system. We have aldehydes and ketones and carboxylic acids. So,
Professor?
yes.
I actually do have a question. It was for chapter 12 review. I didn't understand the nomenclature question on there. It was 5,5-dimethyl. I think it was well, it started on the first carbon instead of the carbonyl group, and I didn't understand why it started there, not on the carbonyl group.
Then you put the carbonyl on the lowest possible number, but you have to have the carbon on the other side of the ketone is also part of the parent chain. So if it was a ketone, the carbonyl cannot be on the number 1 carbon because you have other carbons in the chain. It can be on the number 2 carbon and move over, for example. Okay. So if you had something like this, right here, our longest chain is going to be 1, 2, 3, 4, 5. So, but we still have to number it 1, 2, 3, 4, 5. So that puts our ketone on the number 2 carbon and our substituent on the number 4 carbon. So that'd be 4-methyl pentanone.
Okay. So then for the aldehydes, does it start on the carbonyl then?
On the aldehydes, you start with that aldehyde carbon as number 1.
Okay, I think that was my confusion.
And that's also true for carboxylic acids. That carbonyl carbon is always number 1 on carboxylic acids because carboxylic acids are the highest priority.
Okay, thank you.
Okay. So that's subtle difference, but it's true. Okay, so then we learned that we had alkanes and how to name them, and then we have alkenes, that double bond. That double bond changes the reactivity, okay? And in that double bond, we see that we get a lot of addition reactions. We're gonna add something to one carbon and something to the other carbon of that double bond. And we added acids across there, hydrogen, HBr, and HCl, and that was hydrohalogenation. We could also add water across it. That's hydration. And we can add halogens across it. So you get 2 halogens added on there. That's halogenation. And remember, they all had kind of different mechanisms on how they did it. Okay. Then hydroboration was backwards from the other two. The boron actually ended up on the less substituted carbon. And in hydrogenation, it just adds hydrogen across the double bond by itself. And that's usually catalytic hydrogenation with a solid metal catalyst. Okay. Now, let's see. So that's what we learned in our alkenes chapter, but we also learned about our reaction coordinate diagrams. And what that tells us is what's happening in the reaction. And we learned about 2 different types of reactions. We learned about one-step reactions or concerted reactions where it happens all at once. Think SN2, because both molecules are present in the transition state. So SN2E2, the base and the molecule are there at the same time. Okay. If there are 2 steps, then that means we formed an intermediate. And most of the time we think about E1, E, and SN1 because we form that carbocation first. That's the first step, that highly active intermediate. Then it has to go to a second step. Okay, so we'll look at those like addition reactions can be 1 or 2 steps. Depending on that, if you formed the carbocation, it's a 2-step addition reaction. If you didn't form the carbocation, it's a 1-step concerted reaction. And then we learned that there's only a few things that can happen at any step in a mechanism. You're looking for 5 things, okay? Number 1, add a proton. If you have a negative charge or you have a low space, you have a lone pair, add a proton. If you already have a positive charge, you can take away a proton and make a neutral again. Or you can react an electrophile and a nucleophile, or Lewis acid, Lewis base. Same thing. An electrophile is a Lewis acid, a nucleophile is a Lewis base. So that can form a new covalent bond. You can rearrange. Remember, carbocations rearrange to make the most stable carbocation. Or you can break a bond to form a stable ion or molecule. That's what happens in the first step of your SN1 and SN2 reactions. So there's only 5 things that we're going to look for happening in these reactions. And you take it back to the carboxylic acids. If we had an acid in there, we added a proton. If we had base in there, we took a proton away. Look at the enolates. We added base. We took a proton away to create a negative charge. All of these patterns happen in all of the mechanisms we use. And so, and even the radical reaction. We break a bond to form a stable molecule or ion. In that case, we're making that radical. And so the pattern even follows for our newest mechanism. So look for that continuity in thought process on every single reaction we do. Okay. Carbocation stability. Carbocations are most stable in their tertiary form because all of the carbon and hydrogens in their spy can help support that empty p orbital. Remember, the whole reason it's flat, we have this empty p orbital above and below, and these can help stabilize that empty p orbital, which is why tertiaries are always more stable. And if you have a secondary and you can move a methyl group or a hydrogen, you will rearrange to form that more stable tertiary carbocation. All right, questions about carbocations or reaction diagrams? Remember, a lot of these we did form carbocations and we did form those intermediates. So. And that brings us to that contrast between SN1, SN2, E1, E2, right? SN1 and E1 are always in competition because you always form that carbocation. In SN2, E2, you have better nucleophiles or stronger bases because you have them both there at the same time trying to do the whole reaction at once. Okay, that got us into stereoisomers, okay? The first thing we learned is that things have isomers. And if they're just hooked together differently but the same number of atoms, those are constitutional isomers. Those are different compounds. But then once we had the same connectivity except that two of the things are swapped in space, now we have what is called stereoisomers. Stereo meaning in space. Okay. And we learned that there were different types. If we only have one carbon center that has 4 different things on it, we would have what we call a pair of enantiomers. Okay. That pair is non-superimposable mirror images of each other where everything lines up, but 2 of the groups are swapped. Okay. And they always come in pairs. If you have more than one stereocenter, now you have sets of diastereomers. Okay. And when you look at your diastereomers, if you have non-superimposable mirror images, then you have a set of enantiomers. But if somewhere in your second set of isomers you have a mirror plane, it takes away all of the stereochemistry and turns it into a meso compound. Okay. So that's why we started with enantiomers looking for mirror planes. And then when we move to diastereomers, if we find one, that takes it down to the number of different isomers we have. The other thing to remember is enantiomers are identical in all their physical properties except for rotation of light. Diastereomers actually can be different melting points, boiling points, etc. But the enantiomers within the set of diastereomers should be identical in those properties. Okay, let's see. SN1, SN2, E1, E2. You're going to focus on SN1 with your good to moderate nucleophiles. Once you get to poor nucleophiles, think SN1. It has to wait for the carbocation. Okay, and so we're looking for things that have a good negative charge. All of the good ones have a negative charge and are polarizable. Okay, sulfur is big and fluffy. Bromine is big and fluffy. Iodine is big and fluffy. And then the oxygens are also very good nucleophiles. Now, if we move down to where that negative charge is not localized on one area, or we have something that are smaller ions, they're not as good. And notice in that moderate, we also have what we would traditionally call Lewis bases. They just have lone pairs, but they're big, they're polarizable in their function. And in the last set, all of those are oxygen compounds that are not charged, are poor nucleophiles. So there should be some, rationale to that, and thinking about it in that way, you can guess on whether or not it's a good nucleophile or a poor nucleophile based on those rules. Now, once you use it as a nucleophile and substitute something, you can make most of the functional groups we've talked about, except for the carbonyl compounds, which you have to make by oxidation, or the alkenes you have to make by removing acid. Okay, and then this table here, kind of working this through in your head as to what we're going to see. Big bulky base, think E2. If you have an unhindered thing, you might be able to do substitution reactions with bases, but most of the time they're going to do elimination reactions. If you have a weak base but a nucleophile, you're almost always going to do those substitution reactions. Poor nucleophiles are the only ones that'll compete SN1, SN1, E1, but only on secondary and tertiary substrates. So there's a series of that in there as well. All right, questions on E1, E2, SN1, SN2? Okay, that brings us up to alcohols. And what we learned about in alcohols is that hydrogen bonding is the key factor that changes their properties more than anything else. The only thing that changes more is carboxylic acids because it can hydrogen bond in more ways. So it has the highest change in properties due to that. And we learned that we could dehydrate alcohols, remove water. But if it's a primary, it's kind of hard. If it's a secondary, it's easier, a little bit easier, but if it's tertiary, it's much, much easier, okay? And we can think about that as it's easier because of the formation of a tertiary carbocation or a partially positive charge, making it easier to remove. Now, whenever we do these dehydrations, we always try to make the more stable alkene. That's Zaitsev's rule. The more stable alkene is the one with more things bonded to it, okay? If you have a difference between a disubstituted alkene and a trisubstituted alkene, the trisubstituted alkene would be the major product because it's more substituted. Then we learned we can oxidize alcohols to give us carbonyl compounds. Primary alcohol will only give an aldehyde with PCC, but it'll give carboxylic acids with all the other oxidants. Secondary alcohols give rise to ketones. And this is wrong. I can't believe I haven't fixed it. That's tertiary alcohols give no reaction. Then we learned we can also make alcohols by opening up the epoxy by attacking it with a nucleophile. Any nucleophile will open that up to give you an alcohol on one carbon, and then the nucleophile attached to the other carbon of the epoxy ring. Okay. Which brings us to benzene. Remember, there's rules with benzene. You have to have 4 rules to be aromatic. It has to be in a plane. Every atom in the plane has to have a p orbital. It has to have the right number of electrons, the 4n plus 2, or 2, 4, let's see, that would be 2 electrons, 6 electrons, if n is 8, 10 electrons. So it has to have the right number of electrons, and it has to be flat and in a ring. So those are requirements for aromaticity. But we have different names for these too. So memorizing the names circled here is important. But because of the aromaticity, they don't react like double bonds. They react like benzene rings because they want to substitute out a hydrogen for some electrophile, okay? So we can substitute a hydrogen for chlorine, we can substitute it for nitrogen, we can substitute it for sulfur, we can substitute it for an R group or a carbonyl group. But they all require a catalyst right here. They all require a Lewis acid catalyst because the first step is to generate that positively charged electrophile. So in the case of chlorine, we had to use aluminum chloride to create a positively charged chlorine. In the case of nitrating, we had to create a positive charge on nitrogen. So that's the first step in every single one of these. Then the benzene ring acts as our nucleophile, reaches out and creates a new sigma bond, which is not very stable because it'd rather be aromatic. So it's going to move that positive charge around the ring until it can remove a hydrogen and re-aromatize. And that's step 3. So we have generation of our electrophile, which is usually the positive charge, always the positive charge. And then we re-aromatize. Because of that re-aromatization and where that positive charge goes, we have direction. The second thing adding to it is going to be directed by what the first thing is. And we saw that there was a common theme here, is that all the things that are orthopair directing either were carbon or had a lone pair. Okay? All of these have lone pairs, and the ones that can donate more of their lone pairs are more strongly activated. Okay? These don't donate as much because we have a carbonyl taking some of those electrons away. These are weakly activating because there's a little bit of pull. Now these are deactivating because of electron pull, but the lone pair makes them orthopair directing. So that's the common thing. Lone pair makes them ortho-para-directing. And notice all of the deactivators have carbonyl compounds or a positive charge or a partially positive charge. Okay? That's going to make it hard to put that positive charge on certain sites, and therefore it's a meta-director, and they all deactivate. Okay, so there's a common theme within that set, and if you remember the common theme, you should be able to pick out your ortho and para-directors. So in chapter 10, we talked about the different types of amines. We actually have 4 kinds of amines: aliphatic amine, aromatic amine, heterocyclic aliphatic amine, heterocyclic aromatic amine, and they all had different basicities. The aliphatic amines are always more basic because the lone pair is stuck on a single nitrogen. As you get to more aromatic things, their basicity decreases because it can share electrons with the ring. Okay, so aliphatic amines are always more basic than the other systems. And because the electronegativity difference between hydrogen and nitrogen is less than that of oxygen and nitrogen, it does not hydrogen bond as strong. And therefore the properties aren't as greatly affected. Questions on that? So the amines was a real short chapter. But that brings us up to spectroscopy. We had 2 kinds of spectroscopy. One was IR, and then one was NMR. And the thing to remember about IR is these zones. We're looking at individual bonds, not functional groups. We're looking at individual bonds. A heavy atom, light atom bond are the highest frequency, 2,000 to 4,000. Triple bonds is also a high frequency. It's next, 2,000 to 2,500. Double bonds are next with a higher frequency than single bonds, and then the single bonds are the lowest frequency possible. And again, if the bond is present, it's going to absorb in these. So if you see a peak in that area, that means that that bond type is in that compound. And so whatever compound you choose has to have that bond type in it. Okay, so you're looking for what's there. And let's say one of your compounds has a no peak in the 2,000 to 2,500 range, and one of the choices is an alkyne, you know it can't be the alkyne because it's missing one of the types of bonding in our compound. Which also, well, then we went and instead of looking at individual bonds, we're now looking at connectivity. Okay, so here we're seeing which hydrogens are near which hydrogens in proton NMR. And the 4 things you need to worry about there are the number of signals. The number of signals tells you how many different types of hydrogen you have. Okay, not different numbers of hydrogen, different types of hydrogen. The intensity tells you the number of hydrogens you have of each type. So if you have a signal and you have 2 signals and one says that it's 100 and one says that it's 50, that means you have a ratio of 2 to 1. Okay. Then position, how far away from 0 it is. The further away from 0 it is, the more de-shielded it is, and there's a pattern to it. The more as you move away from carbon or hydrogen, hydrocarbon-like structure, you move further away from 0. And so know the 4 parts right here. Part 1 is the 2 different types of peak. Part 2 is the integration of the peaks. Part 3 is the shift of the peaks. And then the last thing is splitting. Remember, it's n plus 1. So we get 1 peak for the hydrogens themselves, and then n peaks for the number of hydrogens within 3 bonds. So there's 1 peak for this. There's 3 hydrogens within 3 bonds. That's 3 plus 1. Means there should be 4 peaks for that, and we see that in our signal. All right. But in carbon NMR, all we care about is the number of unique carbons and their relative shift. And the relative shift, even though it's much bigger in ppm, it goes to like 200 or 210, the relative positions are similar to that of the proton in the mole. So for example, things with aromatic rings are going to be way out here, things with alkenes are going to be here, things bonded to oxygen are going to be here. But the unique ones are the carbonyl compounds, because carbonyl compounds themselves, except for aldehydes, don't show up in the proton NMR, but they do show up in the carbon NMR very high, above 160, all the way up to 210 for aldehydes and ketones. Okay, so that's spectroscopy, which takes us up to chapter 11. Okay. Are we going to be able to look at past exams to see what we missed to use that as a study for trial? Only if you make an appointment with me and we review it online together. We don't want to have I don't release the exams because of the way they're on Top Hat. I can't release them. But I can talk you through them individually. The last piece of review material that's on Canvas that you probably should look at is I have the organic nomenclature all separated in its own little thing with all the different rules on it. Now it's present on that other one too, but it's here as a separate thing just in case you want to use it as a separate additive. And the last page of this is something I haven't shown you since we did nomenclature, but this is the entire, every possible compound we can do from its lowest priority to the highest priority, and what the suffix names and prefix names for all the different functions groups we did. Even some we didn't really do very much, like the sulfonic acids right here, but aldehydes, esters, all the carboxylic acid derivatives, aldehydes, ketones, they're all here ranked in order. So this is something that I think, you might not need, but I just thought I'd put it in there just so that you, if you had a question, you could go, oh yeah, okay, there it is on the priority scale. That's what it should be. So that's a different page you might not have seen before. All right, questions on nomenclature. Okay, at this point, we have about 20 minutes left. So if you want to stay around and ask questions, please do. If not, go forth and study specifically for exam 3 first, and then start doing the other chapters for our final. Okay, so I will at least be watching to make sure you're getting stuff done on the next 2 Thursdays. So that's it. Are we having a review session on Tuesday, next Tuesday? Oh, no, we do not. I cannot have class on next Tuesday. I think it was a reading day or something, because our exam is on because our exam is on Thursday and our finals also on Thursday. So no review on Tuesday. All right, I'm going to go ahead and stop recording.